Okay, chapter 18, day 1. The focus for this is what are sampling distributions for proportions? All right, sampling distributions, not what we did earlier, which was a distribution of our sample. This is called a sampling distribution, and we'll explain what this means. So in class, we did some dice rolling again, where 1 through 5 was success and 6 through 20 was a failure. But the difference this time is we didn't count how many successes, we counted what proportion of the time we were successful. And so you took how many successes, in this case, out of 5 rolls, and you gave me a decimal, and I marked everyone's data. And then we put our green arrow down, which kind of indicated where it's centered, all right? And all of these distributions that I'm going to show you, we call sampling distributions for proportions. Now, one of the big things here is that each one of these x's is a proportion. How many out of 5 converted to a decimal did you get correct? This green arrow really represents the average of the proportions. And so we signify that with mu sub p hat. So this is the average of proportions, is what that is. It is the balancing point of these proportions, mu sub p hat. So we did sample size 5. We did sample size 10. And again, I drew all of these on the same scale. So same scale, same scale. And again, this is the mean of all the p hats that we had. And again, each one of these was your proportion of how many successes out of 10. And we did it again with 40 rolls. And our data looked as follows. And again, this is the balancing point, or what we would call the mean of all the p hats. Now, we made observations. If you look, they're all drawn on the same scale. They all have the same number of people doing the activity. And you can see that as the sample size went from 5 to 10 to 40, the distribution, the variability in that distribution got smaller and smaller. So as n got larger, the standard deviation for the distribution of proportions got smaller, and that's because of that law of large numbers again. As you do events over and over and over, the probability that you're getting should get closer and closer to the true theoretical probability. All right, so that's because of the law of large numbers. The other thing is, because we are 5 out of 20 success, and that's 1/4 or 0.25, we would expect our balancing point to be 0.25, and it's not initially. And as n got larger, look at the green arrow, moved in a little bit closer to 0.25, moved in very close to 0.25. And so also, as n got larger, the mean of the distribution of proportions, that mu sub p hat, gets closer to the true theoretical proportion, what we call capital letter P. So we know it theoretically should be 0.25, and again, as n got larger, our mean of the p hat, our green arrow, got closer and closer to 0.25. Did it mean that everyone got 0.25? No. It just means if I did this over and over, that distribution will have some variability, but the mean of that distribution should be very close to the theoretical proportion of 0.25, and the standard deviation will shrink as we take larger sample sizes. In this case, our largest was 40. So that brings us to 2 formulas. we know that the mean of a distribution of p-hats should get very close to the theoretical proportion, the true proportion. All right? And the shape started becoming more normal looking as n got larger. So if you look back, look at the shape. Skewed right, still skewed right, starts to get more normal looking as n got larger. Okay? So the mean heads towards the true proportion and the shape starts becoming more normal looking. Because it's becoming more normal looking, we can start to apply normal calculations. So, the mean of the distribution is equal to the true proportion, and the standard deviation is similar to the previous formula, but now that we're dealing with proportions, the standard deviation of this distribution of proportions is going to be equal to the square root of, and all of this is under the square root, p times 1 minus p all over n, and all of that under the square root symbol. And that's the standard deviation. So what do we know? As n gets larger, this fraction gets smaller, and the square root of a smaller number becomes even smaller. But it's mathematical in how it works. If you want to decrease the standard deviation, you have to increase the sample size. Bring this up. Followed by how much? Well, you increase the sample size by the square of the fractional amount that you want to decrease by. So what fractional amount do you want to? You want to cut it in half? Well, then your denominator is a 2. Square that is 4. You would increase your sample size by a factor of 4 to cut this number in half, because the square root of 4 is 2. If you want to get this 1/3 as large, well, the denominator is a 3. Square the 3, you would multiply your sample size times 9 to get it to cut into 1/3. So, cut standard deviation by 1/3, you increase n by a factor of 9. Whatever it is, multiply times 9, and your standard deviation will be as 1/3 as large. Now, again, these formulas, if I'm going to use normal approximation, they only work if I meet my conditions. First condition, I have to make sure that I randomize somehow or have what we consider to be a representative sample. So go back to the start of the school year. Did we represent the sample well, or did we do a randomization process? One of the two. Either there's randomization, or we're going to have to assume that how we did our data collecting gives us a representative sample. Condition 2 was our old condition 1. It deals with independence. Is the situation independent, and or is the population greater than 10 times that sample size? So there's two types of independence here. There's independence, for example, like if I'm drawing cards, every time I draw a card, the outcome of one draw doesn't affect the next. If I am asking someone a question in that situation, let's say I'm looking at cars, and I'm checking on to see whether or not a car stops fully at a stop sign, and I'm trying to figure out the proportion of cars that stop fully at a stop sign. Well, I have independence from car to car. Each car is independent. But again, as I'm sampling, I can only sample one car once, and then I don't sample that car again. So I still have to make sure that the population of cars that I'm pulling from is greater than 10 times my sample size. So if I'm in a region like Greece and I sample 100 cars, I'm going to assume there's more than 1,000 cars that I could have picked from. And every car is independent. Okay? The last condition, still the same, is checking n times p and n times 1 minus p, making sure that both of those are greater than or equal to 10. And if I meet all my conditions, I say it's okay to use the normal model. And then, from the given information, I can calculate my mean, I can calculate my standard deviation, I can put it on a normal curve, I can calculate a z-score, and I can finish out the problem, but this whole problem would be done in percentages, not how many successes. And that's chapter 18.